Okay, good morning, everyone. We we start again with the module regarding the part which is focused on the fuzzy theory and the main operations. So we, in the previous part of the slides, we saw that there are the definition of a fuzzy set and how we can explain it, and now the main operations. And in this slide we saw the negation, so what we call also the complement of a fuzzy set. So that if the fuzzy set is this one in gray, its complement is very easy to understand because is from a mathematical point of view. If you remember that the fuzzy membership function is something which is a domain between 0 and 1 minus this membership function represent the complement of this fuzzy set, which is represented in red. So it's something that is 1 minus, is quite simple. It is normally is indicated as with a bar upper the capital letter. Well, the intersection is something that can have different definitions. The most used one is the intersection. You know, from a graphical point of view, is very clear because you select the part of the graphics of the membership functions that intersects the two common tails of this triangular, almost, they are trapezoidal membership functions. From a mathematical point of view, one possible operation is to find the minimum of the two membership functions. So it's very clear for each x you need to find, so imagine a line which moves from 0 to infinity and intersect starting from where the two fuzzy sets intersect, and you take the minimum, and from here, and then now the minimum is when the part is intersecting of B, of course, is the minimum if B, and when A is intersecting B, the part of the minimum is A. So this triangle, almost triangle, is the intersection. There are other intersection operators. They are called in as a technical term T-norms. T stands for triangular norms. Another is not only, as I already mentioned and highlighted, the minimum. You can find, for example, instead of the minimum, perhaps is something that needs some computational effort, you can use the multiplication, which almost give, of course, they are not nonlinear operations. There was also the what we call with the name of its developer or proposers. Bounded difference is something more complicated because it's the maximum between 0, because the membership function, you know, needs to be always positive. So when you compute the summation of two membership functions, because one can be bigger than 1, so you can have something which is bigger than 1, or can be negative, because, for example, if these two membership functions are lower than, I don't know, very small, you have something very small, -1, so you must guarantee that this operation is always between in the domain 0 and 1, or there are other t-norms. Everything is indicated here as Cartesian products of something of the domain between 0 and 1 to a codomain between 0 and 1. We have another important operation, so they are, as you easily recognize, is something that it belongs to the traditional operations among sets. The union, or is called also disjunction, because it removes the, if you remember, the intersection, so it's something which is called disjunction, and it is clear if the intersection was the minimum, the union is the maximum. So is one, again, is one possible operation, because what we call we have other union operators. For example, a probabilistic, they are called, is called, as for the intersection was the probabilistic, and here we have the probabilistic OR, and so the union is something, as you can easily understand, that provides that the summation of the two sets, fuzzy sets, minus the intersection. Or again, the operation defined by this guy, the bounded sum, so again, is something that needs to be between 0 and 1. So again, you have something that is obviously provided by, so it's a comparison between the minimum of 1. Of course, this can be bigger than 1 or always positive, so you need to find the minimum between 1, or if this summation is bigger than 1, you take always 1, so it's guaranteed that this operation is always between 0 and 1. Or again, there can be other coticonorms. We will see a demo when we will use the toolbox of the MATLAB tool. Of course, the problem is that we are not working with one-dimensional sets, but normally we work with, unfortunately, with multi-dimensional domains. So it means that our sets, fuzzy sets, have at least 2 dimensions. As in this case, you see here that the membership function, in the simplest case, because you can easily notice that if you want to represent it in a 3-dimensional space, you need to consider at maximum 2 dimensions as an input domain. So this set is defined as the membership, 2-dimensional membership function with the inputs given by x and y, where x and y belongs to the Cartesian space x and y. We can also, which is useful in order to, you will see later, to obtain this picture, the cylindrical extension. Cylindrical extension, from a graphical point of view, is very simple, because it means that this operation. So you take each point on this plane. So for each x1, you take the point and you extend according to the second domain, x2. So you have what we call cylindrical, because it's orthogonal to this space. So it's something from a graphical point of view is very clear, and the extension of, according to the, in fact, is you see here, in the x2 direction of A is defined, I don't want, but it's just the definition, the set of all membership functions mu A with x1 with input domain x1, x2, where x1, x2 belongs to this space. So this is the definition. So we can come to the concept of projection, which is something which is related with the extension, because if you start with the, your two-dimensional membership function, you can perform a projection. So it's something, again, quite simple from a graphical point of view, because you can see here the projection according to the variable x1 is defined as a superior. So you take from this shape the maximum value, so the superior or supremum value of all the points of your mu A, this one. So consider the two-dimensional shape x1 or 2 limited on x1. So now, because you are projecting, you are considering x1 when x1 is belongs to this domain. So you take, for considering, so each point in x1, you take the supremum and you find this shape. So a new, as a matter of fact, is a new fuzzy set. And we can do the same onto x2. Of course, if you notice, it has a different shape, because this is the triangular shape and this is the trapezoidal, because in fact is the projection onto x2 is the supremum for all. In the previous case, you take the superior or the supremum with respect to all x2 belonging to x2. So you find all possible x2 by varying x1. On the other hand, you find the supremum by varying all x1 with respect to x2. And you find which is a trapezoidal shape. And now we complete the description by defining the intersection. So the intersection is we will see later, because the intersection represents the relation between two fuzzy sets. So if we have, for example, in this case, again, in a two-dimensional space, because we can represent it in the three-dimensional space, so you can aggregate two, so made the intersection, but in two different domains. So it's not the intersection in the same domain as we saw in the one-dimensional case, but in this case it means that you perform the cylindrical extension. As you can see here, to me is very simple from a graphical point of view. So you perform the cylindrical extension and you find the intersection. Of course, from a mathematical point of view, is a little bit complicated to define this operation, but we will see later how we can solve this problem. Of course, again, this can be is very easy to see in a two-dimensional space, but when, for example, in our case, we are using multi-dimensional spaces. So when we are considering more than two inputs like x1, x2, x3, so it's more difficult to show, so it's impossible because we don't have more than 3 dimensions. So fuzzy relations, we will see something connected to the concept of intersection. So it's why I defined this operation first and then the concept of the relation. So relation, if you think what it means, classical relation represent the presence or absence of interaction between two elements of two or more sets. Well, of course, classical means in the Boolean domain. With fuzzy relations, we are not defining as in the classical concept, in the classical framework, as a Boolean, which means true or false. Fuzzy relations are described again with the degree of association. So is the again is the membership degree. So it's represented by a membership grade. So we have a multidimensional is like this concept. A multidimensional fuzzy relation is a mapping. So as a relation is important, is a mapping. So it's like a function. It's very simply for us, we know, because we know the concept of at least math 1, math 2, so we know what is a function. So as a relation, as a matter of fact, is a function between a multidimensional, so it links n variables, x1, x2, xn, derived from the Cartesian product universe, so it's something related with the Cartesian product space, to a membership grade. So we move from a multidimensional space to a scalar domain. This is the concept of the relation. It's very important. And for example, to me is very clear because we can define this relation. Is also, to me, is quite intuitive because think of the concept x is approximately equal to epsilon. So it means that if you want to represent it also from an intuitive point of view, it can be represented by an exponential variable because this membership function, you know that the maximum, this is a graphical, two-dimensional which represent in black the maximum value when we have here the maximum one. So it's clear that when x is approximately equal to 1, you have the maximum over this line, because of course you know that x is equal to y. So you have the maximum along this line, which is 45 degrees, which represent this value of the membership function. So it's something to me quite clear. So this is a very simple example of fuzzy relation. So x is approximately equal to 1. And as you can see here, it connects, it relates a two-dimensional Cartesian space into a membership function. This is the membership function with values between 0 and 1. So it's quite... So as a, very simply, a fuzzy relation is a function from a multi-dimensional space to a one-dimensional space. And we will use the concept of this relation in order to this is used for the design of a fuzzy model. So we will see in the second part of this module how we can represent, by using these operations, a fuzzy model depending on its form. So given a fuzzy relation R defined from the Cartesian space X multiplied by Y, and a fuzzy set A defined in X, derive the corresponding fuzzy set B defined in Y according to this relation. So it's like, I don't know if you see, it's like a transformation, because the relation is very close to a transformation of a fuzzy set through this relation is transformed into or onto the set B. The operation is quite complicated because it means that you are performing an extension of your fuzzy set A, which is intersecting. So because you know the fuzzy set is a single, as a one-dimensional, so you perform the extension, and its extension, which is here, intersect the relation, which is a two-dimensional set. And in this case, you obtain, as you remember, a two-dimensional, a multi-dimensional set. And then, in order to obtain again a one-dimensional set, you need to project it, this multi-dimensional shape, onto the domain Y, and you obtain a fuzzy set B. So again, you start from A, which is a one-dimensional. You perform its cylindrical extension onto R. R, if you remember, is a relation which is a multi-dimensional space. So you perform the intersection. From this intersection, which is a multi-dimensional shape, you perform the projection onto the domain Y, and you obtain the fuzzy set B. This is the concept of what we call, is quite important because it's something that is used for the design of a fuzzy model. Is called a relational composition. So it's like, again, a transformation. And from a mathematical point of view, is something, as is suggested here, is very close to the evaluation of the function, because if you remember, as I said, you are the intersection corresponds, the operation of the intersection corresponds to the minimum between the fuzzy membership function of A and so the intersection with the multidimensional set this, which is R. So you find the minimum between R and A, which correspond to the intersection, and then the projection, if you remember the concept of the projection, you need to compute the maximum, so that like the boundary, the maximum values of the result of this operation with respect to x, to all the point of x, and you define B, the fuzzy set B. So this is the concept written with the operations, and this is the mathematical computation. It's quite, you can see here it's not so easy, but it's something that fortunately for us is computed by MATLAB or Simulink. Now we come to the concept of the graphical interpretation of a crisp function. You know the concept of a classical function. When you start for the evaluation of the function, you start from its domain, so is the independent variable x, you find its value, and then you find the value y. So this is the evaluation of a classical function, something that is very easy. When the argument is varying between an interval, also the function, so also the function corresponds to an interval, because you have the input which varies in this domain. So according to this function, which is a crisp. Crisp means classical, is a classical function. So let's move to the concept of an interval function. So interval function is used in some domains. It's something, for example, I don't know, in some courses you might have seen something which is defined as a boundary. And in this case, so when you use, for example, it's not our case, but interval function, because perhaps the interval function, I know that, for example, is used by the physicists when, for example, they define a value of a function and something which is related with its accuracy. So you have each point has some uncertainty, so you have an interval function. So in this case, when you are considering an interval function, which is not, pay attention, is not a fuzzy function, is an interval function. So for each independent, for the independent variable x, the output corresponds to an interval now, because of course it's connected to, it depends on the values of the interval. If we have an interval argument, so we have an input which corresponds to a range, is varying between two values, also the output of the function is an interval. So this in the second case of interval function. Let's try to see what happens when we are considering fuzzy relations or fuzzy functions. The fuzzy function determines that, for example, a single value, which is called crisp argument. So now we have to pay attention, because now the function is described with its membership function. So the single value, which is called here crisp argument is this one, is the single value applied to their fuzzy relation. You see here that the output of this fuzzy relation is a fuzzy set, is determined by the membership function, its membership function here. And when we have this symbol indicate which is a fuzzy variable, because it's determined by the fact that the function is fuzzy. So also the output is a fuzzy variable. When we have a fuzzy argument, so the fuzzy argument is what we have as an interpretation of this operation, of the concept of A applied to the relation, if you remember. We discussed what this means. So when A is applied to the relation, so this is the interpretation of a fuzzy relation. So it links the fuzzy argument, that in this case is A, to through the fuzzy relation, which is this one, to B. So we obtain from A is like a transformation. So we have something which is defined by a membership function. It goes through the fuzzy relation, and it is transformed into a fuzzy set B. So this is the concept of the fuzzy relation with a graphical interpretation. So we start from a fuzzy set and we end with a fuzzy set. This is quite important. Let's see how we can perform well, it's not really, to me, for the exam, you don't need to solve this kind of operation, but if you want to compute the composition of a relation, you need to think, for example, just to help you to understand the operation. So when you perform, this is the case of A multiplied by the relation R. As you can see here, we have the fuzzy set A, the relation, which is a two-dimensional space, so is represented by a matrix. And normally, I don't know if it's clear, the operation. So for the case of in order to compute the result here, you make this operation so the output will be a vector with 5 elements. So you are performing this operation, pay attention, because you are multiplying each element of this row for each element of this column. So you compute this operation. The minimum between 1 and 0 is 0. The minimum between 0 and 0.4 is 0. The minimum between 0.1 and 0 is 0 again. The minimum between 0 and 0, 0. The minimum between 0 and 0 is 0. Then, when you compute this first comparison, you need to find the maximum. Which is the maximum among 0, 0, 0, 0 is 0. So the first element of this vector is 0. Let's try with the second element, and then you can see if you have learned the way of computing. Let's try to multiply with the second column. So again, minimum between 1 and 0 is 0. Minimum between 0.4 and 0.1, 0.1. Minimum between 0.1 and 1 is 0.1. Minimum between 0 and 0.1 and 0.9 is 0. Minimum between 0 and 0, 0. Maximum of this column is 0.1. And so on. You perform in this way by computing. And this is the final result. So I don't want to try to. It's clear that why you here you obtain 0.4, because of course when you multiply this for example, for the third column, you have that the minimum is 0.4 and the maximum of this column is 0.4. So here you have 0.4, 0.4, 0.8. I don't want to take all the elements, but let's just examine, and then we have a break, a fuzzy system. So we can define different examples, different prototypes of fuzzy systems. There are three main fuzzy systems that we consider, but we are working with just one of them. There is a fuzzy system defined here as a first point by means of fuzzy parameters. Fuzzy parameters means that the parameters are fuzzy numbers. So it means that, for example, this fuzzy number, it will be represented by, by a membership, like a membership function, I write here, like mu. So the membership function of the fuzzy number 3 will be defined in this way. For example, we have 1, 0, 1, 2, 3, something like that, 4, 5. So you have something which is quite like that. So it's not very nice, but it's something like that. So we have here, you have here the 1. So this is the membership function of the fuzzy number 3. So of course you have that its membership function is 1 when the input is 3, because it's the fuzzy number 3, and it decreases while the input is lower or bigger than 3. This side seems quite clear. This is the example, first example. Well, it's not, we will not consider, we will not use this model. The second one is a system defined by fuzzy inputs and states, and in the second case also we are not considering this prototype, but in this case you have that for this special case, for example, the input and the states are fuzzy sets, and also, as you can see here, the state is a fuzzy number. So this is an example of a state space fuzzy system. So the state will be, in this case, fortunately, is a scalar defined by a membership function of mu of x, So it's as is, I don't know, is value around the value of x and something which decreases. This is the second example. But, well, in our case, we are using this one, a rule-based system. A rule-based system is the most used fuzzy system or fuzzy description because if you notice, it's something which is very close to our description or interpretation of a phenomenon, because with a fuzzy relation you can describe very easily, we will see later, an example of a tank which is filling with water, and in this case you say that if normally a rule-based system is described by means of if-then rules, they are called if-then. This is the prototype if-then rule. We will see later, this is considered the antecedent. So if the heating power is high, then this is a relation, if you can recognize it, then the temperature will increase fast. This is the behavior of your heating system that you have in your house, because when you increase the value of the temperature, your heating system, the heating power is increasing, and then the temperature of your apartment, of your house, of your home is increasing. So this is a very simple description of a process by means of a rule-based system. So this is the the simplest way of describing a behavior of a dynamic we don't know, but normally is dynamic, of a dynamic process. Because you don't need to know the physics behind the process, but from your experience. So it's why fuzzy systems are very known, are very powerful, because even a person who doesn't know anything about physics, but from his or her personal experience, is able to describe the behavior of a process. It's why perhaps now we know that everything is replaced by the artificial intelligence, because it's more common, it's easier to use, but at the beginning, a fuzzy description was very powerful. But it's better than a neural network, because with a fuzzy system, you understand the physics behind the process. With a neural network, if you look inside the neural network, you don't know, you don't see anything. You don't understand anything if you look into a neural network. So I think we can stop here and resume after the break.